power frequency over voltage in power system. So where due to high frequency in the system, the over voltage will be produced with respect to in extra high voltage or ultra high voltage system. So where the voltage will be very high and the frequency is also very high. So what are the causes for this? So if you look at that, in a power frequency over voltage occurs in large power system, where as I mentioned with related to extra high voltage system. So or in other words I can say above 400 kV system, extra high voltage and ultra high voltage system, that is, or I can say in other words, which is the system which is greater than 400 kV. So we say that this power frequency over voltage will occur in the power system. Now what are the main causes for this? So the main causes here with respect to the power frequency and the harmonics over voltage. So the frequency will be very large. Instead of 50 Hz, we may have different frequencies, right? And we may have harmonics within the system because of many power electronic devices connected or many non-linear loads connected to the system. We may have harmonics within the system. So for these two things, what are the main reasons? The first one is the sudden loss of load. The second one is Ferranti effect, and the third one is ground fault and their effect, and the fourth one is saturation effect. So this sudden load, already it is clearly known that whenever there is a loss of load, if due to the fault the load will be released or suddenly the load has been decreased, because of that reason that is called as a sudden load. We will see in detail one by one. The second one, it is called as a Ferranti effect, which will be like unsymmetrical fault which will be present in the system. We will see once again in detail. And the saturation effect is with respect to the transformer here. So overall, if you look into this, the over voltage of a power frequency or harmonics voltage, which is near to our natural frequency or operating frequency, we can say it is a 50 Hz. So it will be near to our natural or operating frequency. So this kind of power frequency or harmonic which will cause the operation abnormally. So which we have Ferranti effect, which may have a ferromagnetic resonance, right? And in the large power transformer, we found this saturation effect also. And we have over voltages due to the capacitors connected in the power system and shunt reactor connected and also transformers connected in the power system. Because of these things, these many effects will be present in the system. So we'll see one in detail one by one. In the first one, that is a sudden load, loss of load. It is also said to be the load rejection. So where the rejection of load is going to happen. So whenever there is a load rejection on a large power system, which causes the speeding of the generator prime mover. So we know that if you take a hydropower system, so where your generator will be coupled to a motor, right? It will be coupled to a motor, where motor will be acting as a prime mover here. So whenever we reject any load, what happens? That load, large load, I am not talking about small load here. So let us take a very large load. Whenever there is a loss of load or a rejected load, suddenly what happens? So that effect will be seen on the generator prime mover speed. So this speed of the generator prime mover will be have a variation. Suppose say the generator speed is rotating at 1500 RPM or something other speed. So that speed is going to have a variation. There will be sudden decrease in the speed or sudden increase in the speed whenever there is a loss of load is going to happen. So that is the direct effect is going to happen on the generator speed of the generator prime mover. And also the speed governor and the automatic voltage regulator will have to restore its normal condition. So this speed is monitored by, we say that, speed governors. Speed governors. This is nothing but where we may make use of different kinds of electric motors. We say special motors. So we make use of this special motor to control the water flow within your turbine. Suppose say I have a turbine here, okay. So where we have a turbine, so we might have seen that. So within this penstock, the water will be coming from the penstock and the water will be falling into this turbine. So this turbine will be coupled to a generator, right. So where the speed of this turbine has to be controlled. So how it has to control? It has to control through the control of water which is falling into this turbine. So this water control can be controlled by a speed governor. So where we will be having a gates to this turbine. So these kind of gates will be present in a circular position. Okay, in a circular position we will be having a gates. So these gates will open and close whenever I want to inject a water with a high pressure or low pressure. I want to open and close these gates. Okay, it will be in a circular way. So where I am unable to show the circular gate here. So the gates will be in this way. So now what happens here? Okay. So here whenever the water falls, we want to control this. Here these gates will be controlled by a speed governor, where these governors will be connected with a servo motor SM. Servo motors will be connected for the entire speed governor, that is the gates of a speed governor. So whenever I give a command for a servo motor to rotate at an angle of 5 degree or 1 degree, so it will move and that much of amount of water will flow into the turbine and the turbine will rotate. Now imagine, because of the sudden loss of load, what happened? The speed has been dropped. Now I want to increase the speed. What I should do? I have to open the gate further. Instead of 1 degree, I may go with a 3 degree. I will give a command for all the servo motors. This servo motor will be connected for all the gates in a circular position to the turbine. So when I give a command of 3 degree or 4 degree greater than the previous value, so it will open much way, so that the large amount of water can flow into the turbine and the turbine speed can increase, and it can restore it to the normal process. So that is where the speed control and the automatic voltage regulation control will be considered. So where they will try to restore to the normal condition. So this explanation will not be present over there. Just I am giving you an explanation how actually the speed control will be done over there in a hydropower plant. So I have to control, I have to bring back to the normal speed. But when you take the initial frequency and the voltage increase, when you take a initial frequency and the voltage increase, we may have a equation. Just I will undo these things. So where the approximate rise in the voltage, whenever there is a fall in the speed of a generator, in that case we may have a voltage increase. There will be a rise in the voltage, and this rise in voltage will be very, very small, even though that can be determined using the equation V is equal to F by F naught into E dash into 1 minus F by F naught into XS into XC. So this is the equation which determines the voltage, the approximate voltage rise will be given in this way. So where the XS is nothing but the reactance of a generator. So this is the reactance of a generator, and XC is the capacitive reactance. It is a capacitive reactance of the line. Whenever any load is connected to this line, whenever we open the load, whenever the loss of load is happening, so that capacitive reactance of the line at a open end and at a increased frequency, whenever you open this load, so whenever there is a change in the speed in the generator turbine, so that will lead to the increase in the frequency also. The frequency, instead of 50 Hz, it may go beyond that. It may go 53, 54, 55 Hz. So that is going to happen over there. And E dash is nothing but the voltage generated before overspeed of a load rejection. So this was a voltage which was generated before any load rejection and before the speed is increasing because of the load rejection. That is the E dash voltage. And F is nothing but a frequency which has been increased. F is nothing but the frequency which has been increased due to the rejection of load. And F naught is a normal frequency. So if you take Indian standard, it will be a 50 hertz. That is my normal frequency. So the increase in this voltage will be around 2 per unit. This voltage will be increased with respect to 2.0 per unit in terms of per unit with a line of 400 kV. If I am rejecting a load with respect to 400 kV line, then there will be increase of voltage of 2 per unit. Just imagine it is a doubling the voltage. If it is a having 100 kV voltage, then 2 per unit meant to say it is going to double the voltage. So this is the voltage will be increasing. So that will lead to huge amount of damages in the system. So the voltage at a sending end is affected by the line length. So where I am sending the voltage to this load, suppose say I am sending the voltage from one of the generator, this sending end the voltage will be affected by the line length. What is the line length? Suppose say I am sending up to say around 5 kilometer line, 5 kilometer length. So based on this length and also the short circuit MVA. So all this short circuit MVA and per unit value. So all these things will be studying in the next semester PSA 1 subject. Okay. And we may have some reactive power generation of the line, and the shunt reactor may also be reduced by the voltage up to 1.22, sorry, 1.22, 1.4 per unit. So this is the short circuit voltage will be present within the system because of the reactive power generation in the line, because of shunt reactor, and maybe because of your some other parameters where the voltage will be reduced up to 1.2 to 1.4 per unit. So if you are making use of these components, this over voltage which is happening because of a rejection of load can be reduced up to 1.2 to 1.4 by adding a reactive power compensation to the line, by adding a shunt reactor to the line. So this is regarding the sudden loss of load rejection. What are the problems will lead to the loss of load in a extra high voltage line? If it is a small line, say medium voltage line, there is no much effect. When we go for a high voltage, then the effect will be very large over there. It leads to the drop in the speed, it leads to the increase in the frequency, it leads to the increase in the voltage. So that will lead to more voltage within the system, and I can compensate this by controlling your speed governor so that I can bring back my frequency to the normal speed so that the frequency will be normal, and also by adding the shunt reactors or your reactive power compensation for the generator, which will bring down this 2 per unit voltage to 1.2 to 1.4 per unit. So the next one is the Ferranti effect. So here, so whenever we have a long line which is uncompensated line, okay, I have a long transmission line, suppose say somewhere I am generating, suppose say I have a 1500 kilometer line, okay, and if this line is uncompensated, I am not providing any compensation for this line. So because whenever we have a transmission line, we give a reactive power compensation, right? We give, we connect few fact devices, we say SVC, that is a static voltage compensator, because what happens when there is a long transmission line, if I have 11 kV voltage here, at the receiving end I may have 10 kV voltage. There may be loss of voltage of 1 kV. If you measure exactly at the midpoint of this transmission line, once again the voltage will not be same. So the voltage will be say 9 kV or once again a 10 kV. So there will be a, because of the losses in the transmission line, the voltage will not be similar. So for that reason, we provide a compensation for the line. So this Ferranti effect is related to the long uncompensated line, which will exhibit the voltage rise at receiving end. So at the receiving end, when there is no compensation, what happens? there may be increase in the voltage. Instead of decrease in the voltage, there may be a increase in the voltage. This increase in the voltage at the receiving end, which is given by the equation. So we say V1 is a sending end voltage, V2 will be your receiving end voltage. Sometimes we may write as a Vs and Vr also. Sending end voltage V and receiving end voltage. So this receiving end voltage V2 is given by the equation V1 by cos beta L. Cos beta L. So where V1 is a sending end voltage and L is a length of a line. What is the length of your line? And beta is a phase constant of the line. Beta is a phase constant of the line. So where this beta is given by the equation. So where beta is given by the equation, that is equal to R plus j omega L into G plus j omega C divided by LC to the power of 1 by 2. So where omega is equal to, where omega is your angular frequency here, where omega is a angular frequency. So this is a equation which gives your secondary voltage, how the secondary voltage will increase due to this Ferranti effect. So now let us see what is this Ferranti effect in, with respect to the diagram. So this is a transmission line. Which is supplied by the voltage V1 and this is connected with a capacitor C and which has a inductance value and the resistance connected in series. There is a line parameters L and R, which is connected once again at a capacitor at the other end of a resistor. So this circuit will continue similarly. So where it is a long transmission line because the Ferranti effect will happen for a only long transmission line. And once again it is connected to a capacitor at a receiving end now. So this is at a sending end. So this entire part is at a sending end and this is at a receiving end. Once again we will be having a at the receiving end L and R. And we have a capacitor once again at the other end of the receiving end and this voltage is said to be V2. This is said to be V2 and this entire length of the line is given by L, which is given by L. L, R, C are the per unit length of the parameter here. So all your R value, L value, C value will be given in terms of per unit and L is the length of the line. So this is a typical uncompensated long transmission line where there is no compensation is provided for the transmission line. So when you consider this kind of line, the line capacitance is concentrated at middle of the line. So these capacitors will be concentrated at the middle of the line when if you have an open condition of the line, whenever there is an open condition in the line at the receiving end, then the line current will be given by the equation, IC is equal to J into omega C into V1. This is also equal to V1 by XC. V1 by XC. So this is a line charging current at a receiving end when there is a open circuit condition, and at the same time the voltage at the receiving end is given as which will be approximately equal to V1 into 1 minus XL divided by 2XC, XL by 2XC. So where XL is your line inductive reactance and XC is a line capacitive reactance. So this is a voltage and current which will be given at the receiving end. So where this will indicate there is a rise in voltage at a receiving end because of the Ferranti effect. And I can write the approximate vector diagram as well as a circuit for this transmission line, for a long transmission line. So just I will erase this. So this is approximate figure for the above transmission line, which can be written in this way, where I have a V1 which is connected with a reactance and with a capacitance, and where this will be your V2, and this is your XL by 2. So I am dividing that XL, entire XL into by 2 because I am taking a midpoint here with a capacitor connected. So where in this capacitor where current will be flowing IC, and this is my XC. And the vector diagram for this circuit will be in this way, where IC is given here and this is my V2 in the x axis, V2. Till this we will be having at this parameter till here to here we will be having where the voltage rise is going to happen, that is the V1 into XL divided by 2 into XC. So till here it will be V1, from here that is a V2. So this part is nothing but V2, that, or we say the receiving end voltage. So this is nothing but a Ferranti effect. So where basically whenever there is a rise in a voltage at a receiving end of a transmission line, right, because of it may be your opening of a line or any other conditions which will result into the receiving end voltage will be higher than the sending end voltage. That is called as a Ferranti effect.